we go. All right. We're going to finish inverses today. I got you kind of on a good path yesterday for knowing what an inverse does. Who wants to tell me what an inverse does to an original function? Undoes it. There you go. That's a good word. All right. And then what's the key aspect of finding inverses, whether it's an equation or a list of ordered pairs? What's the key money step? Switch X and Y. Switch X and Y. Yeah. Now, when you have a graph, we get the graph by reflecting across line Y equals X. So f of X is another name for Y. So if you want to start by saying Y equals, that could be like priming the pump. But the money step is right here. Cha-ching. We get X equals negative 3Y plus 11. Is it possible to go straight from the first step to the third step? Absolutely. Absolutely, if you could do that. All right. Now we're going to solve for Y. So I got to do what first? Divide by negative 3 question mark? Nope. I got to do what? Subtract 11. Okay, so I get that right there. And then to solve for Y, I divide both sides by negative 3, and I get X minus 11 over negative 3. Now, let me talk to you about this right here. This is kind of interesting. Notice I have 3 terms, 2 in the numerator and 1 in the denominator. You see how 2 of the 3 terms are negative? We try to avoid negativity as often as we can, right? It's true in life as well as math. So what we can actually do is multiply both the top and the bottom by negative 1 over negative 1, which is equal to what? What's negative 1 over negative 1? 1, right? And can we multiply anything by 1 without changing its value? Heck yeah. So if I distribute now, I'm going to get negative X plus 11 all over 3. And then we also in math don't like to lead with the negative. We like to bury negatives if we can. So I would call that 11 minus X over 3. That's a much prettier version of my answer. Much prettier. Now, 2 of the terms are positive instead of 3 of them being, or 2 of them being negative, and I've buried the negative in the second term. Now, the last thing I want to do is call that what? Instead of just Y equals, I'll call it what? I could call it Y inverse if I want. But what's the better name for Y inverse if I started with f of X? Yeah, f of X inverse, or as we read it from left to right, f inverse of X. Más mejor que bueno. F inverse of X. And there you go. Right? You found the inverse of negative 3x plus 11. And we didn't do it intuitively. We did it algebraically. All right, comments or questions on that? Did you like that? Has anyone told you Happy Leap Day yet today? Yeah. No. Well, Happy Leap Day again. Happy Leap Day. Today's the last day of February. I'm glad when February is going to be over. It's hard to say. And it's also the last day of cold weather, I think. Tomorrow's supposed to be in the high 70s again, or mid 70s. So enjoy the cool weather one last day. Enjoy February one last day. Because tomorrow's going to be March. March. I have problems saying that one too. March. March? March. February, March. I need to work on my pronunciation of the months. All right. We were on example 2B. 2B. Or was it not 2B? Ah, yeah, okay, good. It was 2B. So what were the instructions? It says to graph and determine if it needs to be restricted and then answer the questions. Okay, what's the parent function on f of X on part B? What is it going to graph as if it's a squared? A quadratic. And what do we call the graph of a quadratic? Smiley face, also known as a parabola, right? Parabola? Okay. What does the plus 5 do to the entire graph, including the vertex? Left 5. Good. And that's the only transformation. So I'm going to come over here. 1, 2, 3, 4, 5. There's negative 5. There's where the vertex is, and it opens up. So it's going to look like this. It's going to look like that. There's f of X right there. My question to you is this, right off the bat. Is that function one-to-one? Nope, it's not one-to-one because it fails the what? Horizontal line test. I have repeated y values. That's another way to tell if a function's one-to-one. If it has repeated y values, it's no good. So we want to keep one of the branches, either to the right or to the left of the vertex, and get rid of the other one. Okay? As a matter of convention, which one do we keep, do you think? To the right of the vertex or to the left? Which one do we keep? We like to keep to the right. By convention, everyone's going to agree that most people, most times, we're going to keep it to the right. which means the little branch over here to the left, he's going to be gone. Now, is the highlighted piece 1 to 1? Yes. Okay, so I got to restrict the domain for all values of x that are what in relation to -5? Greater than, or I could equal -5, yes? So let's go ahead and write that officially over here. The restricted domain is the set of all x such that x is greater than or equal to -5. Now, if you want to know what the inverse graph will look like, you're not going to have to do that, but you could reflect it across the line y equals x and kind of figure out what it's going to look like. It's going to look something down here. Here would be -5 on the y-axis, and then it's going to look something like this. Okay, you don't have to draw it, but it's going to look something like that. Now, it says to find the inverse function, so I need the equation. Okay, I need to find it. So just like we did in the warm-up, we're going to find the inverse. So I'm just going to bring it down here where I can work on it. Can we do 2 steps in 1 here? I got f of x. You want to call it y and then switch them, or switch them while we're calling it y? I think we could probably switch it. So instead of f of x, it's going to be y, but that's going to become x. So here's the money step. And you get y plus 5 equals 2. So that's 2 steps in 1. Okay, now I got to peel back the layers and solve for y. What's the first thing we need to do? Unsquare it. We need to unsquare it. So when I unsquare the right side, I get y plus 5. And on the right side, I get plus or minus the square root of x. Plus or minus the square root of x. Which one do I want? Plus. I want the plus. Yeah. We consider the plus or minus, but we keep the plus deliberately. If you always restrict your graph to the right of the vertex, you can always take the positive version. If we would have restricted our graph to the left of the vertex, now I'd have to go with the negative version down here. So it's just easier to stay positive. All right. Now I just got to solve for y by subtracting 5, and I'm going to switch both sides. So I get the square root of x minus 5. And then the last step we need to do is rename it. What are we going to rename it? Not f, but f inverse. So f inverse of x is the square root of x minus 5. Okay, so there's what we're right over here. So we get f inverse of x is the square root of x minus 5. Now, if we wanted to, we could graph that. If we didn't know what it looked like by reflecting it across the line y equals x, now we could graph it because this is going to take our new parent function. Our new parent function is the square root of x, which remember looks like this. And what would the minus 5 do to that graph, and as well as any graph?
Down 5.
Down 5. 1, 2, 3, 4, 5. Boom. Very good. And there's -5. So if you wanted to sketch it over here, I already had it kind of partially sketched. That I was doing it by kind of reflecting it across that line. But once you find the inverse, you can actually sketch it and then see, oh yeah, they end up being kind of reflections across that line. Oh, look, it gave us a grid over here to graph it. Do we have to re-graph it if we drew them over here? Nah, I'll count that as your graph. I'm not used to using preordained graphs like that. I think they're actually too constricting. Unless you need to be exact because you want to find a specific point on the graph, like if it's linear. If you're drawing curves, I don't really like that. So I just like sketching them like this over here. All the grids get in the way of understanding to me. So I'll accept that if you want to sketch it separately. I have to decide. Okay. Any questions on letter B? Letter B. All right. We're on what, David? What letter? Well, yeah, good. We're on C now. Okay. I just want to make sure. You're way over there. I just want to make sure you're paying attention. You haven't looked up in a while. All right. Letter C, x cubed plus 4. Let's see what that dude looks like. The parent function is x cubed, and we know what x cubed looks like. It's your discograph, right? It's the one that comes in concave down and then goes concave up. What does the plus 4 do to it?
Up 4.
Up 4. So if you want, we can do this in Notability. If you want to draw x cubed in a single stroke like this, if you want to draw x cubed in a single stroke, now all you got to do is grab it and move it up 4. 1, 2, 3, 4. Oh, I lost my arrowhead. I'll move it. There we go. Good. So now the inflection point is at 0, 4. The inflection point is at 0, 4. I'll put a 4 right there. Remember, the inflection point is where the curvature changes. Concave down like a frown to the left. Concave up like a cup to the right. The next question. Is this graph 1 to 1? Does it pass the horizontal line test? Nah or yo? Does it ever touch the graph in more than one place at a time? It passes. X cubed, as we saw yesterday with the parent function, is 1 to 1. If it's 1 to 1, do we need to restrict the domain? No, we sure don't. Okay, so get rid of the horizontal line. Restricted domain, I'm just going to say none or no. None. None. No. We don't need to restrict it. Now we can say what the domain is going to be. What is the domain actually going to be? The unrestricted. Let's write that. The unrestricted domain. What would be the unrestricted domain? What's the domain of x cubed? All negative infinity to infinity or all real numbers? Yeah. So if it ever asks you for the restricted domain, it's not asking you for the actual domain. It's saying what if any values need to be restricted? We don't need to restrict it. Okay? There's no restrictions. All right. Now for the inverse function, we need to go ahead and do what we did before. Switch x and y. So I'm going to go straight to the money step from up top. It becomes x equals y cubed plus 4. Yeah, yeah? That's the money step. Interchange x and y. Now we just got to solve for y. So I subtract 4. And then how do we uncube something? We cube root it. Okay? So the entire x minus 4 now goes under a cube root. And we put a little 3 in the v right there. That means it's cube root. And what can we name it? If you want to name it right away, instead of naming it y, can we go straight to renaming it right there? Absolutely. Let's say it's a line of writing. If you know that's going to be equal to y, you can save a whole line of writing and just call it f inverse right there. Okay? So that's the inverse function. F inverse of x equals the cube root of x minus 4. Make sure that the cube root covers the 4. Like, don't do it like this. Some people get real hasty and they say it's the cube root of x and they come out like halfway over the negative sign. If I see that, do you think I'm going to count it right? No, I'd be like, no, the whole thing has to be covered, sheltered, right? Like an umbrella, sheltering both of them. There you go. Okay, now, do we want to sketch the inverse? Let's sketch the inverse. We know that the cube root of x, okay, let's sketch the cube root of x. The cube root of x comes in like this, concave up, goes vertical, and then goes out like that. That's the cube root of x, okay? Remember, it's curved differently. What would the minus 4, that was good, that was good. What would the minus 4 do to the graph if it's inside the radical, not outside? Is it up, left, down 4? Down 4? Nope. Down 4 would be if it were outside the radical. Right 4. It's on the inside, so it's the opposite of what it appears. So it'll go 1, 2, 3, 4. And the inflection point now is at 4, 0. And now we can label that as f inverse of x.
On the last one,
Mm-hmm.
does the 5 have to be inside that too?
No, because it started on the inside. The 5 started on the inside, so the first thing we did was we took the square root. So now that we take the square root, it's just the square root of x, and now the 5 is on the outside, and so when we subtract, the 5 is on the outside. That's why it's down 5 instead of right 5. Now, if you want to sketch these on the same coordinate grid, just copy this, right? Copy this, paste it over here, right there, somewhere, and this would be the point 4, 0. And now, do those look like they're reflections across the magical line y equals x? They do, don't they? Yeah, if you turn your head at a 45, like you're clapping, but you're really folding. You're clapping like a seal, right? We should try that at the next pep rally. See if I can get everybody to clap like a seal with me all in unison. Hey, did y'all get to go to the last pep rally? Because they got some seniors at the last minute. No? It wasn't all sophomores. I'm sorry, sophomore, not seniors. Yeah, I was about to do the spirit yells, and I was going to do just seniors and juniors, and then someone came up to me, Miss McLean, I forgot her name. Principal, associate principal, what's her name? Does anyone know?
No idea.
Not Miss OG. She's the associate principal. I think it's Miss McLean. She came up and said, "Sophomores are actually here." And I looked around. The stands were like empty. I'm like, "Why aren't all classes here already?" And so I looked around. Where are my sophomores at? And three people, literally, Carson Cox was one of them, raised their hand. "We're over here, sir." And I was like, "Oh, okay. There are the sophomores, all three of y'all." And we did the spirit yell, and they represented. It was actually pretty good, but I didn't know which classes of sophomores they chose to bring to the pep rally at the last minute. It wasn't y'all's, I'm guessing. That's a bummer. Now, here's the good news. For our last pep rally of the year, since they did invite all three classes, albeit it was at the last minute, and there was still plenty of room left in the gym, maybe, just maybe, at the last pep rally of the year, we can get all three classes in the gym at the same time, and we can have ourselves a real pep rally. Yeah. When the stands are empty, it's like when I'm trying to conduct a pep rally, it's like I'm doing it in a morgue. Like no one's reacting. They're just like, "What?" And I cheer. I say, "Get loud," and they're like, "Yay!" Right? Just yay. That's it. I'm like, "Come on, people! Yay! Stand up!" "No, thank you." Right? But when it's filled with people and everyone's there, then it's like, "Well, if you're going to do it, I'm going to do it." Right? So anyway, we'll see. All right, last example. Example 3. Y'all ready? Example 3. Because a inverse function undoes the work of original function, what would happen when we apply two inverse functions back to back? That is, what if we compose them back to back? This is composition. How would you read this? You would read this as of f inverse of x. So here's what's happening here. This is sequential. We start on the inside. We start with x. We apply f inverse to it to get a result, and then we apply f to that result. What should happen when you apply two inverse functions back to back? You should end up where you started, right? For instance, if I stand right here on the floor at x marks the spot, I'm not going to stand. I'm going to pretend like I'm at a pep rally. If x marks the spot, I go 2 steps to the right, and it puts me here, and then I go 2 steps to the left, it puts me back where I started at x marks the spot, right? Because 2 steps to the right and 2 steps to the left, they undo each other. That's exactly the same thing with composition. We're starting with x, we apply f inverse to it, and then we turn around and apply f to it. We're back where we started at x. Now, does it matter the order in which we do it? Could I have gone 2 steps to the left first and then 2 steps to the right? Yeah, so the order doesn't matter. So it works here too. I can start with x, and now I can apply f to it, and then apply f inverse, and I'm right back where I started. Okay? So that's the idea behind composition of inverses. This is the only time composition is commutative, meaning the order doesn't matter. I can do 2 right, 2 left, or 2 left, 2 right. But in either case, regardless, I end up with x, which is where I started. So it says to verify now, you're given two functions, and instead of finding the inverse, it says to verify that they're inverses of each other. So let's go ahead and do this first. Okay, first we're going to do f of f inverse of x. Now, how are we going to start doing that? Well, here's what I'm going to do. I'm going to do substitution. You see how it says f inverse right there? I'm going to substitute f inverse. What is f inverse equal to? Look over here. It says f inverse is what? It's the square root of x plus 3. So is everyone okay with me just substituting that in there? Yeah, I'm just literally replacing f inverse with what it's equal to. Now, here's where it gets fun. I have to evaluate the f function, not at x anymore, but at the square root of x plus 3. So, since this is function f on the outside, function f says to do this. It says input squared. Think of x as just being an input. Input squared minus 3. Think of this as being my input. Okay? So here's what I'm going to do. Instead of x squared, I'm going to put parentheses squared minus 3. In other words, I'm writing this as parentheses squared minus 3. And whatever goes in the parentheses in one goes in the parentheses in the other. What am I plugging in for the parentheses? Not x, but rather Square root of x plus 3. Okay? That's the important thing. Now, once I have it set up like this, all I got to do is evaluate it, and I should end up with what if they're inverses of each other?
0.
Not 0. What did I start with? No, I started with x, right? I started with x. So I should end up with x. Let's see if we get x. What would be the square root squared? What happens with the radical when I square the whole thing? It goes away. So I just get x plus 3, and then I get minus 3. Hey, what's 3 minus 3? So what's x plus 0? X. Did I get x? I did get x. I started with x, and I ended up with x. Now all we got to do is do it the other way. Let's do it in reverse order. Okay? Number 2. Instead of f of f inverse, let's do f inverse of f of x. So again, what are we starting with here? On the innermost part, we're starting with x. We should end up with x. All right, step 1. I'm going to leave this as f inverse of, and I'm going to just replace f of x with what f of x is. What is f of x? X squared minus 3. Very good. Now here is it's not the hard part, but it's the part that requires just a little bit of a leap. I got to plug x squared minus 3 in, this whole thing. I got to plug it into the f inverse function for x. So instead of the square root of x plus 3, I'm going to write it as the square root of parentheses plus 3. Input, okay? And what am I plugging in for my input? X squared minus 3. X squared minus 3. Okay, good. Now that you have it set up, now you can evaluate it. The parentheses were there just to show the substitution. There's really nothing to distribute, so I can actually drop the parentheses. And now what will I do? What's under the radical? What's negative 3 plus 3? 0, so those cancel. And I'm left with the square root of x squared, which is what? Did I end up with x again? I did. And because I got an x both times, it didn't matter if I went left first then right or right first then left. Doesn't matter if I do f and then f inverse or f inverse then f. Because I got x, I'm going to say so. Here's the consequence. So f and f inverse are inverses of each other. If either one of those ended up being something other than x, anything other than x, a number or x squared, then it's game over. They're not inverses of each other. Okay? So that's how you use composition to show that two functions are inverses. You got to plug, you're literally plugging one function in to the other function where there's an x. And then you're evaluating. That's it. That's the whole section. Any questions? All right, so you have the rest of the period, which is 25 minutes to work on your assignment, and your assignment's due tomorrow morning at 9? Yeah, absolutely. Okay, we're done.